Hearty welcome to another lecture from CEC Gurukul. We had been discussing about digital electronics, and wherein we had understood the different kinds of data, that is the bits that are involved in digital electronics. We had in our last lecture talked about storage of these bits in basic memory elements, which we refer to as flip-flops. We had begun with SR flip-flop and come to JK flip-flop. We had discussed the advantages of JK flip-flop over SR flip-flop, wherein the specific case of both inputs being 1 was allowed in JK, whereas it was the forbidden state in SR flip-flop. So what we have here is the case of JK flip-flop with some minor modifications so as to overcome the problem of toggling, as we discussed last time in JK flip-flop when both J and K were equal to 1. What we understand is that in JK flip-flop we split the flip-flop in two parts. One is taken as the master, another as the slave. This is required so that both the flip-flops do not toggle at the same time. As you can see from the figure that we have actually fixed two JK flip-flops in series. So when J is equal to 1 and K is equal to 1, then we notice that both the flip-flops, the master as well as the slave, might have the same input, but the output is not toggling. How do we achieve that is what we are going to discuss today before moving on to the concept of shift registers. If we look carefully, we see that both the flip-flops, the master and the slave, are in series. That is, the input is taken in the master, that is the J and K, and output of the master is the input of the slave. The most important thing to note here is that both the flip-flops will not operate at the same time. Why? Because the clock in J, in the first master flip-flop, is the complement of the slave. If one is positively triggered, the other is in negative trigger. So let's start and understand how toggling is prevented from occurrence in master-slave configuration. When J is equal to 1 and K is equal to 1 is fed as input in the master, then at the first clock pulse, the data moves to the output of the master, which is the complement of the last state, as we had seen in our earlier lectures. Now this output of the master gets instantaneously transferred as the input of the slave, but slave does not work because the clock is the complement in the case of slave. So the input remains fixed and does not propagate to the output in the slave at that point of time. When the next clock pulse comes, that is from the positive clock pulse it goes negative, then the input of the slave, which was the output of the master, is propagated to the output of the slave. But at this point of time, it is very important to note that input of the slave does not change. That's because the master JK flip-flop is disabled. So hence, by sequentially clocking the master and the slave and introducing a propagation delay between the two, one is able to overcome the problem of toggling. When J and K both inputs are equal to 1. So the JK master slave is shown, the diagram is shown like this, where we write JK M/S. Hence, the thing to note here is that toggling is overcome by the introduction of master slave configuration in JK flip-flops. Another way to prevent this toggling is to use in edge triggering. The problem of toggling does not occur in JK flip-flop because edge is much faster than level triggering. Level triggering meant having the clock high or low for a larger extent of time compared to edges. So if we look at this numerical over here, we can see that when J is equal to K is equal to 1, then the flip-flop simply toggles at each time the clock goes low. Why? Because we see that the symbol of the clock is shown as negative triggering. So therefore, we see if we look at the clock, then the value of Q changes at every negative going state. So we all know that when J is equal to 1 and K is also equal to 1, then the output of the flip-flop is the complement of its last state. So initially, as you can see, Q is 0 initially when clock begins. So at the first negative going pulse of the clock, the state changes from 0 to 1 and it remains 1 till the second negative going clock arrives. At this time, the high value of Q goes low. This change of state goes on at every negative going pulse or the falling edge of the clock. So if we have, you can see that if we have a JK flip-flop which is positive edge triggered, then output is shown in this diagram. Initially we see that J is 0 and K is 0. At the positive edge triggering, J is seen to be 1 while K is seen to be 0. Hence, the value of Q changes from initial 0 state, which we have assumed, and it changes its state to being 1. And this goes on till the time when next positive edge comes. At next positive edge, it is important to see, positive edge means also the rising edge. It is important to see that J is equal to 0 and K is also equal to 0. Then from the truth table of JK flip-flop, we know that the flip-flop output is the last state. And what was the last state? The last state in this case was Q equal to 1, and so it is retained. Again, we see that during the third rising edge, we have J equal to 0 and K equal to 1. So therefore, at the third rising edge, the value of Q changes from high state to a low state. Fourth rising edge, we see again J equal to 0 and K equal to 0, and therefore the output is the last state, and the last state was 0, so therefore 0 is to be seen. And in this way we find that the JK flip-flop positive edge triggered has the following truth table and the timing diagram. So in a nutshell, we can summarize: in the master slave configuration, while the clock is high, the master is active while the slave is inactive. And when the clock is low, the master becomes inactive and the slave remains active. So the timing diagram of, again, master-slave JK configuration is shown over here, and we see that it behaves in a perfect fashion. The only thing important over here to note is that we have an enhanced propagation delay compared to a normal JK flip-flop. The reason is very simple, that instead of one JK flip-flop, we are using two JK flip-flops in tandem. So the truth table is shown again over here, and in this case, why is this truth table shown? Because we have introduced two new functions in this case. The first one is a preset, which is denoted by PR. Next one is clear, which is CLR. Clock, of course, we know. J we know, and K we know as the two inputs. So when PR is equal to 0 and CLR, that is clear, is equal to 1, so irrespective of whatever is the state of clock, J input or K input, the output of the flip-flop is fixed at 1. When preset is equal to 1 and the clear is 0, then again, irrespective of the status of the clock or the J and K inputs, the output of the flip-flop is fixed at 0. When preset is equal to 1, clear is equal to 1, irrespective of whatever is the state of the clock, and if J and K inputs are both at 0, then no change occurs in the output of the flip-flop. That is, if it had 0, the output would be 0, and if it had 1, the output will still be 1. Moving on to the concept of shift registers. Now, we had discussed the flip-flop. Why? Because the flip-flops would be used to store a number of bits which together are known as registers or shift registers. Just like the registers in our daily life in academic circles, wherein we note down all the important points, theory and practicals, the shift registers in digital electronics are used to store data and move data, and hence the name shift. The data can be shifted to the left or the right. In due course of time, we will discuss in detail about this shift registers. First, a few definitions. What is a register? Register is a group of memory elements that work together as a unit. A simplest register will just store a binary word. The binary word is a collection of 4 bits. When we buy any register, depending on the number of classes we have, we buy a thick register or a thin register. A thick register has more number of pages to store data, which will be our for classwork, which may be our homework, which may be our rough copy, which may be our practical file. Just like that, depending on how much data we want to store and process, we make use of the size or interchange the size of the register. There is another component that is known as a counter. This counter is actually a special kind of shift register which is designed to count the number of clock pulses that have come in. The counter may be a count up counter or a count down counter. A typical example being in a petrol station. When we take the fuel for our vehicle, we see that it is an up counter. That is, the amount of fuel being dispensed also counts up from 0 to some particular value, as also the money that we need to pay. A typical example of count down counter is the pocket money that we get at the start of the month or the salary. So that is countdown counter, because as the time passes by during a month, our amount of money keeps reducing as we spend for different things during course of time. The third thing that is important to understand where registers are used is the buffer register. This buffer register is actually a temporary register which we use to great extent in our computers, which temporarily stores data for processing. Typical example being, suppose we copy a certain amount of text or a picture and we have to paste it somewhere. So therefore we use a buffer register. Even when we play games, computer games, then we store a lot of data which we require temporarily for processing, which is lost as soon as the application is closed. So henceforth we will be discussing in detail the different kinds of applications that we have with this shift registers, the counters and buffer registers. An example of buffer registers that is built with positive edge triggered D flip-flops is shown in this diagram. Now we have used many words to define this diagram. First thing is the buffer register. The moment we say buffer register, 2 or 3 things should be very clear to us. Number one, this register is able to store data temporarily. That means we can write in data, we can read the data, we can remove the data and feed in new data. From the diagram we see that there are 4 edge triggered D flip-flops, and the symbol for the clock indicates that they are all positive edge triggered. Why? Because there is no bubble associated with the clock. Had there been a bubble associated with the clock of the flip-flops, then it would have been negative edge triggered D flip-flops. We go back a couple of lessons ago, we discussed the D flip-flops. Now what are D flip-flops? D flip-flops are, or D flip-flop is a modification of SR flip-flop, wherein we ensure in the SR flip-flop that both the inputs, that is S and R, cannot be same at a given point of time. With SR flip-flop, we know it has 2 inputs and hence 4 combinations. As a recap, let's discuss the SR flip-flop. SR flip-flop inputs are S and R. When they are 0, 0, then the output of the flip-flop is the last state. It can be 0, it can be 1. S is equal to 0, R is equal to 1, output is 0. S equal to 1, R equal to 0, output is 1. And finally, S equal to 1, R equal to 1. Now this state is forbidden in SR flip-flop. So hence we understand that there are only 2 input combinations wherein S and R are not equal. That is 0, 1 and 1, 0. So D flip-flop is modified SR flip-flop with only 1 input that ensures that SR flip-flop, S and R are always complement of one another. So another important thing to summarize from here is that what is the maximum amount of data we can store in this configuration. If each flip-flop stores only 1 bit, as we have seen thus far, any flip-flop will store only 1 bit. Therefore, having 4 flip-flops implies that the biggest data we can store here is 4 bits. That is, in decimal terms, if we have the digital, there are 4 inputs here, hence there will be 2 to the power 4 combinations, that is 16 combinations. So minimum value of the word will be 0, 0, 0, 0, and the biggest value of this word will be 1, 1, 1, 1. Hence, in decimal terms, we know that this flip-flop combination as shift register can store values from decimal 0 to decimal 15. 0, 0, 0, 0 is 0 decimal, and 1, 1, 1, 1 will be 15 in decimal terms. So this buffer register can have any data from the inputs. The inputs in this case are x3, x2, x1, x0. You can name them as anything, A2, A3, A2, A1, A0. We always read from MSB towards LSB. Hence, the inputs could be B3, B2, B1, B0 as being 0, 0, 0, 0 to 1, 1, 1, 1. So, in this case, what we say that the output of this buffer register, that is Q3, Q2, Q1, Q0, is equal to X3, X2, X1, X0. The circuit is a bit primitive because here no controls are shown to process the data, which actually is shown in this case. In this case, we find that it is the previous circuit itself, with the only difference that input, that is the D input of each flip-flop, is coming through a combination of two AND gates and one OR gate. Output of the OR gate is fed directly as the D input. So D3 has an OR gate as its input. D3, D2, D1, D0 all have their inputs coming from OR gates. If you look at the diagram carefully, then we have that both the inputs of the OR gate, we have a 2-input OR gate here, and both the inputs of the OR gate are coming as outputs of two AND gates. Now these two AND gates, it is a very symmetric structure. In digital electronics, everything is modular. So if you have to increase bits, or you have to increase processing or decrease processing, we have to remove everything or add everything in a modular fashion. We have a clear signal here. We also have clock here, which is fed simultaneously or at the same time to all the D flip-flops. We also have a signal called load. As you can see, the load signal is fed to one of the AND gates, that is on the right, and its complement is fed to other AND gate, which is on the left. So the moment we have this configuration, it is clear to us that only one AND gate will work at a given point of time and other AND gate will be inhibited, because we know that AND gate gives a high output if and only if all of its inputs are high. So we take a break here and come back in the second edition of this lecture. Thank you.